welcome to the tutorials on dynamic system modeling and control. This particular tutorial looks at fundamental analogies between mechanical and electrical systems. The goal here is to take what you've learned in terms of developing state space models of mechanical dynamic systems and use it as a bridge to teach you how to develop state space models of electrical dynamic systems. Once more, my name's Hussam Fethi and I'm happy to be going through this tutorial with you. I have three goals in this tutorial. The first one is I want to show you some fundamental analogies between signals in mechanical and electrical systems. When I say signals, I generically mean any quantity that is a variable with respect to time that changes as a function of time. So velocity as a function of time is a signal, force as a function of time is a signal, current, voltage as a function of time. These are all signals, okay? And I want to explore the analogies between the signals in a mechanical system and the signals in an electrical system. I want to use that to leapfrog and basically study the fundamental analogies between the elementary components of mechanical and electrical systems. We're going to discover analogies between inertias and inductors. We're going to discover analogies between capacitors and springs, resistors and dampers, and so on. And so I want to see how the components of a mechanical system are similar, fundamentally similar, to the components of an electrical system. Finally, there's going to be a little bit of a teaser towards the end of this tutorial. I'm going to throw a problem at you where your goal is to use fundamental analogies to derive a state space model of a simple electrical circuit. If you're watching this tutorial because you're taking ME 450 at Penn State, this is something we're going to do in class as a quasi-classwork exercise. If you're watching this video tutorial for other reasons, this is a little bit of a brain teaser to get you to really think about these fundamental analogies. So these are the three goals of this tutorial. So let's start with the first goal, exploring fundamental analogies between signals in mechanical and electrical systems. Before we dive into that, an important caveat or side note: there are actually multiple ways that you can construct analogies between mechanical and electrical systems. You can look at variables and classify them into flow variables versus effort variables, which is what we're going to do. You can also look at variables and classify them into through variables versus across variables, which is not something we're going to do. The particular set of analogies we're using in these tutorials is inspired by something called the bond graph language. I'm not going to incorporate within these tutorials a formal introduction to the bond graph language. That's slightly beyond the scope of the tutorials. However, I would really like you to know that the analogies that are being presented in this tutorial are grounded in a fundamental theory called the theory of bond graph modeling that we will not go through formally, but we'll still learn a lot of its underlying lessons as we go through this tutorial. So with that in mind, what I want to do is I want to think about a very generic mechanical component and a very generic electrical component. The generic mechanical component can be just a translating mass or a spring or a damper. Applied on this mass or spring or damper is a net external force, perhaps a net external torque, and as a result of the application of this force or torque, the mass, spring, or damper has a translational or rotational velocity. Now, when I say applied on the mass is a force, I'm not necessarily saying that this force is an input variable. I'm not necessarily saying that it's an output variable. All I'm saying is there's a mass and there's a force acting on it. And as a result of this force, there's motion and there's velocity. Now, if we think about a generic electrical circuit component, say a circuit component that you put on a breadboard as you construct a circuit. Examples of generic electrical circuit components include inductors, capacitors, resistors. Applied on this inductor, capacitor, or resistor is an electromotive force. Another name for an electromotive force is a voltage. And as a result of this voltage, there is a current that might flow through this component. When you look at these two diagrams, you begin to realize, you begin to see three very big insights. The first insight, the first fundamental insight or key insight is that there is an analogy between the motion of mass electrons. They're both motions, they're both, in a sense, flows, if you use a very expansive definition of the term flow. In other words, velocities, translational or rotational, and currents are fundamentally analogous. They're all flow signals, they all quantify motion. Now, not only do these velocities quantify motion, this motion is induced through a forcing mechanism. And this forcing mechanism could be a force in a translational mechanical system, or a torque, or an electromotive force in an electrical system, meaning a voltage. So the second key insight is that forces, torques, and voltages are also fundamentally analogous. They're all effort signals. They induce the motion, they induce the flow. And then the final key insight, if you pay really close attention, in a translational mechanical system, the effort variable is a force, the flow variable is a velocity, the product of force and velocity is power. In a rotational mechanical system, the effort variable is a torque, the flow variable is an angular velocity, the product of torque and angular velocity is also power. In an electrical circuit, the effort variable is voltage, the flow variable is current, and the product of voltage and current is power. In watts, they all have the same units, they all give you power in watts if we're using SI units. In other words, flow and effort variables come in dual pairs. I'm not going to define what this means formally, I just want you to understand it intuitively. They come in dual pairs whose product consistently has units of power. With these three fundamental analogies between signals in the mechanical and electrical domains, now we're ready to begin to explore fundamental analogies between components of mechanical and electrical systems, elementary components of mechanical and electrical systems. When we think of elementary components of a mechanical system, we think of masses, inertias, springs, dampers. When we think of elementary components of an electric circuit, we think of inductors, capacitors, resistors. And the question I want to ask here is, in what ways are these components essentially the same, fundamentally the same? In what way do they essentially do the same thing? Well, let's take a dive straight into that question with an example. Let's ask ourselves, the mass, the inertia in a mechanical world, what is analogous to that in the electrical world? And the answer is the inductor. We need to talk here about something called the generalized inductor, also sometimes known as a generalized inertia. It is a generic component that represents a mass in a mechanical system, or a rotational mass, an inertia in a rotational mechanical system, or an inductor in an electrical system. These components are all the same. To see how they're all the same, let's think about a mechanical mass and what it signifies. A mass is essentially an object on which you apply a force. Let's say that the net external force is F, and as a result you get a velocity V. The governing equation of motion for the mass is F is equal to ma or mv dot, assuming that the mass m remains constant. So in essence, a translational mass represents a static relationship between force on the one hand and the derivative of velocity, also known as acceleration, on the other hand. You notice that the translating mass represents a static relationship between an effort variable, force is an effort variable, and the time derivative of a flow variable. That's what a mass is, that's what it represents. Now, when I say a static relationship, there's significance here to the use of that term. What I'm saying is, when you say F is equal to ma or mv dot, you don't need any further derivatives or integrals. Once you've taken the time derivative of the flow variable, the relationship now is static. There are no further dynamics, there's no need for further differentiation or integration. Okay? Now, if you think about Newton's laws of motion, one thing they say is that a body at rest remains at rest, and a body in motion remains in motion at a constant speed unless acted upon by a net external force. Now, if you think about what that means, masses like to travel at a constant velocity. They resist changes to this velocity, and the only way that you can change their velocity is to apply a net external force on them given by F is equal to ma, or mv dot. By resisting changes to their velocities, the masses are essentially telling you something. They're telling you that they remember the past. They remember the past through velocity as a memory variable. They remember the past by storing kinetic energy. And the kinetic energy they store is given, as we all know, by half mv squared. Now, all of this is plain vanilla, very elementary high school physics, basically perhaps even middle school physics. Now what I want to do is I want to take these relationships here and these facts that I've put on the slide, and I want to rewrite them one more time in the rotational domain, and then rewrite them one more time in the electrical domain. So let me erase the statements that I have on the slide and rewrite them in the rotational domain. What is a rotational inertia? If I use the exact same language, I find out that a rotational inertia is a static relationship, again between effort and the time derivative of flow. This statement has not changed even one bit. I just replaced the word mass with a rotational inertia, and I changed the meanings of effort and flow within parentheses. The effort variable in this case is a net torque. The flow variable is an angular velocity, and the time derivative of the flow variable is an angular acceleration. But apart from that, there is still a static relationship between effort and the time derivative of flow. As a matter of fact, if we think of a rotational inertia acted upon by a net torque T and having an angular velocity omega, we know that T is equal to J, the value of the rotational inertia, multiplied by d omega by dt. And it's the exact same equation as Newton's second law of motion, where F is analogous, force is analogous to torque, mass is analogous to J, the rotational inertia, rate of change of linear velocity, translational velocity with respect to time is replaced with rate of change of angular velocity with respect to time. So now let's move to the second statement. What does a rotational inertia like or dislike? Well, the same way that a mass likes to translate, at a constant velocity, a rotational inertia likes to rotate at a constant angular velocity. And it resists changes to this velocity by basically applying a resistance torque back on anybody who's trying to change its velocity. So in order to change the velocity of a rotational inertia, you have to apply a torque equal to j omega dot. Finally, what this means is that the rotational inertia remembers the past by storing rotational kinetic energy, and the equation for kinetic energy is exactly the same. 1/2 j omega squared instead of 1/2 mv squared. So far, again, I haven't shared anything particularly profound with you. There's just an analogy between translational masses and rotational inertias. Now we make a slightly bigger leap, still not a huge leap, but a slightly bigger leap, when we recognize that these two kinds of components are analogous to an inductor. So let's think about an inductor and what it represents. Again, the statements don't change. I've replaced the word rotational inertia with inductor, but still, an inductor is a static relationship. It represents a static relationship between effort on the one hand and the time derivative of flow on the other hand. In this case, effort is voltage, and the time derivative of flow is current. We know when we have an inductor with a current I flowing through it and a voltage V across it, if it has an inductance L, V is equal to L times di by dt. The effort variable V, which is analogous to force, analogous to torque, is equal to a constant inductance L, which is analogous to mass, analogous to rotational inertia, multiplied by the rate of change of flow, current, with respect to time. Okay? Now, an inductor is essentially a device that produces a magnetic field by having current pass through its coil. It doesn't like to see this magnetic field change, and therefore it doesn't like to see the current change. It likes to maintain a constant current, and it resists changes to this current. What's really interesting, if you think of current as a flow variable, this is analogous to saying that a mass doesn't like to see its velocity change, and it resists changes to its velocity. These components all like to see constant flow, and if flow changes, they basically get a little unhappy with you. And the inductor remembers the past by storing electromagnetic energy, and the energy it stores is 1/2 multiplied by the inductance L multiplied by current squared. Moving on from the concept of a generalized inductor and the fact that it's analogous to masses, analogous to a rotational inertia, the next thing I want to explore is the analogy between springs on the one hand and capacitors on the other hand. I want to introduce the notion of a generalized capacitor. A generalized capacitor is a generalization of this idea of a spring, or this idea of an electrical capacitor. So let's talk about springs. A spring represents a static relationship between effort on the one hand and the integral of flow as opposed to the derivative of flow on the other hand. So for example, a spring gives you a static relationship between force and translational displacement in the translational world. It gives you a static relationship between torque and rotational displacement in the rotational world. In the translational world, if the force acting on the spring is F and the displacement of the spring is X, F is equal to K times X, where K is the stiffness of the spring. This, of course, assumes a linear spring, but I just want to use this as a representative relationship to say that there is a static relationship between effort, force on the one hand, and time integral of flow, time integral of velocity, meaning displacement on the other hand. The spring likes to maintain a certain undeflected length in translational springs or a certain undeflected angle in rotational springs. And if you try to twist it or compress it or extend it relative to that undeflected length or undeflected angle, you get a reaction force. And the reaction force is governed by the spring law. It's governed by, if the spring equation is F is equal to K times X, if you try to deflect the spring by distance X, it reacts to you with a force F, which is equal to Kx. Finally, the spring remembers the past by storing elastic potential energy, and we all know the equation for elastic potential energy is 1/2 kx squared. Now what I want to do is I want to take these exact same statements and I want to completely rewrite them for a capacitor. So let me erase these statements and rewrite them for a capacitor. Again, we find that a capacitor represents a static relationship between effort on the one hand and time integral of flow on the other hand. Effort in this case is voltage. Time integral of flow. Flow is current, and the integral of current with respect to time is charge. So a capacitor is a device that gives us a static relationship between voltage and charge, and that is indeed true. For a linear capacitor, the relationship is that voltage is equal to 1 over capacitance multiplied by charge. You notice that that's the same equation as the spring equation with one small caveat. Voltage is proportional to force, is analogous to force. Charge is analogous to displacement, but capacitance is analogous to 1 over stiffness, or stiffness is analogous to 1 over capacitance. So in order for these two equations to look the same, F is equal to Kx and V is equal to 1 over C times Q, we have to think of capacitance as being analogous to compliance as opposed to stiffness, or as being analogous to 1 over stiffness. Having said that, the statements are still the same. The capacitor likes to maintain a state of charge of 0, just like the spring likes to maintain a deflection of 0. And if you charge the capacitor, you get a reaction voltage. The capacitor remembers the past by storing, I'm going to loosely use the term here, electric potential energy. And electric potential energy, just like elastic potential energy, is 1/2 multiplied by stiffness, which is equivalent to 1 over C, multiplied by displacement squared, which is equivalent to charge squared. So it's 1 over 2C times Q squared. So here we see how capacitors are analogous to springs, inductors are analogous to inertias. The thing that's left on the electrical side in terms of an elementary component is a resistor. On the mechanical side, the thing that's left in terms of elementary components is a damper. Resistors and dampers are indeed analogous, and we will refer to them as generalized resistor. Let's start with a mechanical damper. A simple pretend that it's linear just to keep the equation simple. It could be nonlinear. A simple damper represents a static relationship between effort on the one hand and flow on the other hand. Notice I'm not taking derivatives or integrals of flow anymore. So, for example, in the translational world, a damper applies a force on me that is proportional to translational velocity. In the rotational world, I get a reaction torque that is proportional to rotational velocity. So the equation is essentially F is equal to C times V, or torque is equal to C times omega. The force F is equal to some sort of a damping coefficient multiplied by velocity. Dampers dislike motion. They don't want to move, or they don't want to have relative motion between their two ports in the case of a mechanical damper. They produce a reaction effort, a reaction force, or a reaction torque that is proportional to the speed of this motion. Now, what's interesting is you notice because this equation doesn't have any memory operators in it whatsoever, dampers actually do not have memory, and they do not store energy. And so we don't have an equation for energy storage because dampers are not energy storage devices. They dissipate energy. In much the same way, if we were to take these exact same statements and rewrite them for a resistor represents, again, a static relationship between effort and flow. Effort in this case is voltage, flow is current. So a simple linear resistor is governed by V is equal to R times I. Voltage V is analogous to force. Resistance R is analogous to damping coefficient. Current I is analogous to velocity. The resistor dislikes the flow of electricity, and it produces a reaction voltage in proportion to, or that is statically related to be a little more precise, because the resistor could be nonlinear, to the current flow. Resistors do not have memory, and they do not store energy. So now we've come up with fundamental analogies between masses and inertias on the one hand and inductors on the other hand, between springs on the one hand and capacitors on the other hand, dampers on the one hand, resistors on the other hand. There's one more component that I want you to think about, and I'm not going to spell out the fundamental analogy for that component for you. I want you to think about it and come up with it on your own. I want you to think about a pair of gears, a massless, frictionless, perfectly meshed pair of gears in the mechanical world, rotational mechanical world, and an electric transformer. Now, both of these devices essentially either amplify effort and reduce flow. So they increase torque, or they increase force, or they increase voltage at the expense of reducing velocity, translational or rotational. In the case of translational velocity, of course, we're talking about something that is more than just a gear pair, perhaps a couple of rack pinion mechanisms or something like that, that allow us to have a relationship between two different translational velocities, a proportionality relationship between two different translational velocities. But in both cases, you're amplifying effort and reducing flow, or amplifying flow and reducing effort in a manner that essentially conserves energy. So the question is there a fundamental analogy between them, between gear pairs and electric transformers? Can you create a slide that is similar to the presentation slides you've just seen, exploring the notion of a generalized transformer? That's my first teaser for you. Now I'm going to throw an even bigger piece of food for thought at you. I want you to think about a very simple rotational mechanical drive. Very, very simple. It has an inertia J1, and you're applying a torque T on it. Think of this as the input torque. This rotational inertia is attached to a massless pair of gears of radii R1 and R2. This pair of gears drives a shaft. The shaft is actually long and skinny enough to the point where it's compliant, and it has a stiffness, a rotational stiffness K. This shaft in itself now pushes or applies a torque on another inertia J1 about it, um, this is a very simple rotational mechanical system. You've derived state space models for it before if you're taking ME 450. And you derive these state space models using your understanding of mechanics, of basically equations of motion and kinematic relationships for a very simple mechanism like this. But wouldn't it be neat if you could draw, based on what you just learned, an analogous circuit that has the same dynamics, that behaves in the same way, that has the same governing equations of motion? Wouldn't it be neat if that circuit's input could be analogous to the input of this mechanism? If that circuit's output could be analogous to the output of this mechanism? Wouldn't it be neat if you can write down the state equations for that electrical circuit and convince yourself that they're essentially the same as the state equations, the state and output equations for this mechanism? I'm going to leave it at that. This is your exercise, classwork teaser, if you will. And I'm just going to say this. Our goals for this tutorial were to explore the fundamental analogies between signals in the mechanical and electrical domains, and also to explore the fundamental analogies